Hey guys, welcome back to another video. In this video, we're going to talk about how to find cell potentials of different electrochemical cells. That is, your electrodes can be made up of anything. So, for example, over here, we've created an electrochemical cell using an electrode of magnesium. That is, we have a magnesium ion half cell. We also have another electrode that is a calcium electrode, which is a calcium and calcium ion half cell, right? So we're going to see how we can find the cell potential of this entire cell using the electrode potential of each of this half cell, right? Fair enough. So I'll first up explain the setup of this entire electrochemical cell. So on one side, on the left hand side, you have a magnesium ion half cell. That is this reaction, this half equation. You have an electrode made up of magnesium metal. In the solution, you have 1 mole per dm cube of magnesium ions. How can you bring 1 mole per dm cube of magnesium ions? You can take any compound, that is, let's say magnesium sulfate, and you can dissolve it in water to create a solution of magnesium ions, right? So you can dissolve 1 mole per dm cube of magnesium sulfate to get 1 mole per dm cube of magnesium ions. Great. Now the other side, you have the right hand side where you have a calcium. Why did I write? Right. So you have a calcium electrode and you have a solution of 1 mole per dm cube of calcium ions. How did we make 1 mole per dm cube of calcium ion concentration? We basically used a solution of calcium sulfate. You can use pretty much anything to create 1 mole per dm cube of calcium ion concentration. So since the ratio over here is 1:1, therefore 1 mole per dm cube of calcium sulfate will also give us 1 mole per dm cube of calcium ions. Now let's say, for example, if the ratio, let's say this calcium to sulfate, which is not, I'm just giving you an example. There are cases where the ratio between the metal and non-metal is not equal. So let's say if it was calcium to sulfate, right? In that case, you would only take 0.5 mole per dm cube of calcium sulfate. Why? Because for each mole of calcium sulfate compound, you get 2 moles of calcium ion. Therefore, this 1 calcium sulfate will break down to give you 2 Ca2 plus ions, which is why when you would use anything with an uneven molar ratio between the metal and non-metal, you'd have to be careful about the concentration. So in this case, you would have to write 0.5 mole per dm cube instead of 1. However, calcium sulfate, 1:1 ratio between the metal and non-metal, which is why 1 mole per dm cube. Fair enough. So in this case, you have the calcium solution inside. You have the calcium electrode, and it has its own equilibrium. This has its own equilibrium. When you connect both of these together, you will see electrons will flow from a place of greater accumulation to a place where it's relatively more positive, right? So high negative charge, low negative charge. Where does electron flow from? From here to here. Okay. Now let's understand how to find the cell potential. That is what will be the reading on the voltmeter. That is what we are going to figure out over here with this example. Okay. Oh, right. Another thing, you also have to draw the salt bridge. In the last video, I gave you an example of what the compound could be in the salt bridge. It could be, let's say, potassium nitrate. There are also other examples, but you could use, let's say, potassium nitrate. So what it will do is basically if the ion concentration over here decreases, so the potassium will replace the ion concentration to make sure your ion concentration does not change, or let's say your positive ion concentration does not change. I'll explain the purpose of Sol bridge later on again, but the summary of how Sol bridge is useful is it replaces the concentration of any used up ion. Therefore, if here the calcium 2 plus ion concentration decreased, the ions from the Sol bridge would go to the solution and replace that concentration such that it remains 1 mole per dm cube, right? So that is the whole purpose of having a Sol bridge. Okay, now understanding the equation at each electrode, you have the magnesium electrode, where notice the electrode potential over here is minus 2.38. Notice the electrode potential at calcium minus 2.87. Now, which one do you think is more negative? Obviously, the one of calcium, right? Minus 2.87. Therefore, since more negative, it will want to give its electron away, right? It will want to give its electrons away. Now, what do you call giving your electrons away? For this, calcium wants to give its electrons away. So, it is becoming oxidized, right? So, what can we say about this part of the half cell? Sorry, what can we say about this part of the cell? We can say oxidation is taking place over here, right? Oxidation is taking place over here. Now, where does oxidation take place? At the anode. At the anode, right? The other thing, again, for the magnesium electrode, what is happening? Notice it is less negative. That means more positive, which means it wants to gain electrons. Therefore, the reaction will take place forward, meaning reduction will take place in this case. Mg2 plus will gain electrons, gain 2 electrons specifically to form magnesium atom, and it will deposit on this electrode, right, over here. So you'll see magnesium atoms being deposited on the surface of the magnesium electrode. Why is that happening? Less negative, therefore it wants to gain the electrons, and hence you'll have what will you have? You'll have reduction taking place, right? It will gain the electrons, therefore reduction taking place. And where does reduction take place? At the cathode, right? At the cathode reduction takes place, which is why this will be your cathode, this will be your anode. The other thing is, notice which electrode is positively charged and which electrode is negatively charged. So they might ask you to add a sign to which electrode is positive and which electrode is negatively charged, right? Now, in this case, notice over here for the magnesium half cell, it is less negative. Therefore, compared to this half cell, it should be the positive terminal. And this should be your negative terminal, right? And what do you know about conventional current? Goes from positive terminal to negative terminal. Therefore, your I, representing conventional current, moves from the Mg electrode, magnesium electrode, to the calcium electrode. However, your real current, meaning the flow of charge, flow of electrons, goes from the negative electrode to your positive electrode, right? So be careful about when they ask you to denote the direction of flow of current, real current or conventional current. Be careful of that, because depending on that, you will draw your direction, right? Wherever the positive terminal is, the conventional current will flow from the positive terminal to the negative terminal. In case of real current, flows from the negative terminal to positive terminal. And how do you find the positive terminal? Whichever is relatively more positive or less negative, that will be your positive terminal. Great. So those few things we are somewhat clear about. So the other thing I'll talk about is about how to write the electrode potential reactions. That is your half cell reactions. Now, I'll give you the exact context that is from the data booklet. Notice all of these reactions are written in terms of reduction. So if I take an example, the first one, silver ion gaining an electron to form silver atom, right? Now, in this case, you can see it goes from oxidized +1 to an oxidation state of 0, reduction taking place. In case of the second one, aluminum, you can see +3 gains 3 electrons, aluminum atom. Therefore, in all of these examples, reduction is taking place. And in case of your electrode reaction, that is electrode potential reaction, all of the reaction are actually in terms of reduction. Therefore, all the cell potentials are given in terms of reduction. Now, notice, even in our case, what we are supposed to do is write our electrode potential reactions in terms of reduction only. Now, you might argue that if at the, let's say, at the anode, if oxidation is taking place, shouldn't I write Ca turning into calcium ion plus 2 electron? Yes, that makes sense. You're supposed to. However, since our electrode potentials are given in terms of reduction taking place, we will be writing our equations only with respect to reduction. Now, let's say in case of magnesium ion, it gains 2 electrons to form magnesium atom, right? So in our case, is that happening? Yes. Therefore, it is a forward reaction. Hence, reduction is taking place. In case of calcium, is calcium ion gaining 2 electrons? No. In our case, oxidation is taking place. Therefore, it is a backward reaction. It is a backward reaction, meaning oxidation is taking place. Now, why is it useful? You'll see when I calculate the electrode potential. In that case, this way of writing is going to be useful, since all of the electrode potential values are given in terms of reduction taking place. So whenever you write your electrode potential, electrode reactions, you're going to write in terms of the reduction process. Now you can, for your sake, you can, on the side, you can write oxidation or reduction to remember what is happening at each side. I usually draw an arrow to understand what is exactly happening. But yes, this is how you're supposed to write your electrode reactions. Fair enough. Now, notice when you have a more negative electrode potential, that value suggests that the element on the right-hand side tends to lose electrons readily, a good reducing agent. Therefore, if the value is more negative, in our case, calcium, that means the species on the right-hand side of our equation is going to lose electrons. It is more prone to lose electrons, right? Therefore, it is a good reducing agent, because notice, if it is more prone to lose electrons, that means it itself will get oxidized, but in the process, release electrons. These electrons can be used by the magnesium to be reduced. Therefore, it's a good reducing agent. Quite oppositely, in case of a more positive electrode potential value, it suggests that the ion on the left-hand side tends to gain electrons more readily. Therefore, a good oxidizing agent. Therefore, your species on the left-hand side is going to gain electrons readily, right? So, if it is going to gain the electrons, it is going to be reduced. Therefore, since it is taking away the electrons, it has to take the electrons away from another species. Therefore, this species or atom is going to be oxidized. Hence, a good oxidizing agent, right? Therefore, again, all of these electrode reactions are written in terms of reduction because our values are with respect to reduction taking place. Our standard electrode potential values are given in terms of reduction taking place, which is why when you're going to write the equations, always write it in terms of reduction. Now, in our case, we started off the video asking how are we going to find the cell potential of this electrochemical cell. So let's now find that out. Let's calculate it. So we know where is oxidation taking place over here, right? It's going to lose the electrons. Why? More negative electrode potential, right? Fair enough. Now, where is reduction taking place? Over here. Is going to gain the electrons, forming the solid. Okay. Now, if I try to find the value of potential difference, I'm going to be using this formula. I'm going to be using this formula which denotes the electrochemical cell potential is going to be the electrode potential of the reduction and the electrode potential at the anode, right? So over here it's actually supposed to be cathode. I don't know why I wrote reduction. You could also write electrode potential for reduction and electrode potential for oxidation. So you can substitute cathode and anode for oxidation and reduction. Anyways, so this is your equation for finding the difference in electrode potential, which in return will give you the electrochemical cell potential. That is the potential difference between two electrodes. That is between two half cells. So you're going to write what your electrode potential is at the cathode. So what is your electrode potential at the cathode? Minus 2.38. Minus 2.38. What is your electrode potential at the anode? It is going to be minus 2.87, right? Minus 2.87 at the anode, right? Okay, so electrode potential of cathode minus electrode potential of anode, and that is going to give you minus 2.38 plus minus plus 2.87, and that is going to give you a net electrochemical cell potential of 0.49 volts. Therefore, if you connect these two half cells together, the voltage measured by the voltmeter is going to be 0.49 volts, right? Now, notice one thing. Between the cathode and anode, there is a negative sign. Now, you may ask me, why is the formula written in this way? Why is the electrode potential at cathode, why is the electrode potential at anode subtracted from the electrode potential at cathode? The answer is, remember, all of these values are given in terms of reduction. That is why you need a minus sign over here. Why? Because notice, at the cathode, reduction is indeed taking place. So you will definitely take minus 2.38. However, at the anode, oxidation is taking place. Reduction is not taking place, which is why you will be adding a minus sign such that it can change it into a positive sign, meaning oxidation is taking place over there. Therefore, plus 2.87. Therefore, this is why you need the negative sign between the electrode potential of cathode and anode, because of the anode over there, oxidation is taking place. And remember, I mentioned all of these values, these electrode potential values are given in terms of reduction, right? So therefore, whenever oxidation is taking place, you need to add this negative sign. to denote oxidation is taking place over here. So when you calculate, you can find the exact potential difference between two half cells. The other thing is, you'll notice these circles on top of the E sign, that is the electropotential sign. So these basically mean standard conditions. The standard conditions again are 298 Kelvin, 1 atmospheric pressure, and 1 mole per dm cube of ion concentration. Right? So granted, all of these conditions are met, you can make this calculation to find the potential difference between two half cell equations. And that is going to be it for this video. If you want to see how to calculate electrochemical cell voltages, that is cell potential, I have one video that I've created in this playlist solving a few questions from electrochemistry. So I'll link the playlist in the description. You can go to the playlist and watch that video to understand how to solve questions with this formula, that is how to find the electrochemical cell voltage or potential difference. So see you in the next video.